Hello there, folks. Welcome to another exciting edition of HO Chemistry Flipped Classroom. This is Mr. Los, and we're going to be talking about metallic bonding today. What could be better? I wish that was just a little bit above that line. Sorry if that bothers you. All right, now, before we do that, you don't need to write this down or anything, but let's just review a little bit about how ionic bonding works, because definitely going to be talking about metallic bonding and kind of comparing and contrasting the two types of bonding. So remember, ionic bonds are transfers of electrons, and what results there is a crystal lattice where we have positive and negative charges, and they're lined up. This is positive, this is negative, and they join up and they form this structure called the crystal lattice, which we see here. And we're going to see that metallic bonding do kind of form a lattice of sorts, but it works a little bit differently. But just kind of keep that in the back of your mind as we go through and talk about metallic bonding. All right, folks, let's get ready here. We're about to drink from the fountain of knowledge. Like this young guy here, he's struggling a little bit, but gosh darn it, he is trying to drink from the fountain of knowledge. That's all I can ask of you guys. We're going to try to understand this. We're going to try to get through it, and I think we'll do it. All right. So now if you think about it, if you take something like, oh, I don't know, this paperclip right here. This paperclip is probably made of aluminum, or mostly aluminum. There has to be something holding these aluminum atoms together here in this shape. Otherwise, I couldn't be holding this paperclip, because if there's nothing holding these aluminum atoms together, they would just be flying all around the room everywhere. So that force that's holding these aluminums together in this paperclip is a metallic bonding, or any metal object you can think of, whether it's a soda can or a spoon or steel girders. The thing that's holding those atoms together in that shape is known as a metallic bond. This is true whether we're talking about pure metals like a nugget of gold or something, or we're talking about alloys, which we'll get into. But things with metallic bonding are generally not considered compounds. You know, you can have metal elements like gold, iron, lead, or alloys, which are considered mixtures. So this is a little different than the other kind of bondings other types of bonding that we've talked about. We're not talking about forming compounds here. We're just talking about forces that hold together metals. Something I just want to mention, just because it gets brought up, and I want to make sure you understand what these things are. I don't know what in your imagination, like where we get aluminum or where we get copper or iron or the other elements. I think some people kind of imagine just like dig up a chunk of copper out of the ground. That's not the case at all. What we do is we look for rocks that have, in the case of iron containing compounds in them, or copper containing compounds. And we do some chemistry and we extract the metals out of those rocks. So we got hematite, arginite for silver. That's the hematite right there. That's the arginite. So if you're in the business of mining for silver, you're looking for rocks like this, and then you're getting the silver out of those rocks. And those are called ores. And not something it doesn't say in the syllabus that you specifically need to know about ores, but it does come up. So I just want to make sure that term is something that you know. But anyway, how metallic bonding works is metals, we've talked, have lower valence electrons compared to nonmetals. Have loose valence electrons and lower ionization energy, is what I mean to say, compared to other elements. So those valence electrons in a sample of a metal, so imagine like a sheet of aluminum foil, they tend to become delocalized, in other words, not associated with any particular atom. So if you can imagine, if this is a sheet of aluminum foil, those are my little aluminum atoms. Those are aluminum atoms' valence electrons. They're just kind of flowing all around the sheet. No one particular metal owns them. So because of that, there's going to be a positive charged core remaining. If aluminum loses its 3 valence electrons, it's going to have a little +3 core behind. So these delocalized electrons, the bond actually happens between these delocalized electrons and this cation core. That's what's sticking the atoms together. That's what's holding this paperclip together, is the free-flowing electrons that are wiggling in between the cation cores, opposites attract, it all sticks together. The bond is considered non-directional, term brought up in your syllabus. It just means the electrons are, all electrons, it probably should say, are attracted equally to all ions. So there's no particular direction to this force, as opposed to an ionic bond, which we'll kind of talk about in a second. So these delocalized electrons, if you think about metals, and what we're trying to do as scientists is we're trying to see things that we notice about metals, like, hey, Metals are bendy, and they conduct electricity or whatever, and a couple other things. We have to develop a model of metallic bonding that can account for those properties. And this model of metallic bonding does that. So, for example, metals are malleable and ductile. Now, if you're not familiar with these words, malleable maybe, but especially ductile. Malleable just means you can bend something without breaking it, as opposed to brittle. Like clay is malleable, a clay pot is brittle. Ductile means you can make wires out of these things. Malleable is the more important word. Make sure you know what malleable means. Make a note of that if you don't. But basically, so again, let's imagine this is a sheet of metal and we apply a force. We can cause these atoms in the metal to shift, and the metal will bend without breaking. Now, all metals are malleable to a degree. Some of them at room temperature are not very malleable. You might have to heat them up to get them to wiggle around a little bit. But all metals are malleable to a degree. Now, this doesn't work, again, contrasting it to ionic bonding. This doesn't work. Imagine how our crystal lattice is here. It's very, very important in the case of a crystal lattice where the bonds are, where the ions are. So, for instance, in sodium chloride, sodium is positive, chlorine's negative. They're right on top of each other. We've got a chlorine over here, we've got a sodium down here, and all that stuff. So it's always positive, negative, negative, positive, and so forth. If you apply a force and you shift the whole kind of one row of the lattice over, not only positive, positive right next to each other, or negative, negative, like charges repel and the lattice will fly apart. So ionic substances are not malleable because there is a directionality to their bonding, and it's very important where one ion is relative to others. This is not the case in a metallic bond. You just got these cation cores, you got the electrons wiggling all between them. So it doesn't make any difference where the atoms are relative to each other, or not as much difference as compared to an ionic bond. Another very familiar thing and why metals are useful is they conduct electricity. Now, we've talked a little bit before about like ionic substances. They conduct electricity when you dissolve them or melt them. What you need to conduct electricity is charged particles that have the ability to move. So if you think about ionic bonding, if you think about metallic bonding, that's exactly what we have here. We have these electrons, which normally, if it's just a piece of metal sitting there, all these electrons are just kind of wiggling around randomly. But if we apply a voltage or an electric potential difference, now we're going to expand more on what that means when we do electrochemistry in year 2. But basically, when you apply a voltage or you hook a metal up into a circuit that's a wire, these randomly moving electrons, you're basically just getting them to move in one direction and get them to go where you want them to go. So since we have these charged particles that have the ability to move, this model of metallic bonding allows us to understand why it is that metals can conduct electricity. Oh, hey, it's Mr. Dog. What do you think of this metallic bonding stuff, Mr. Dog? Well, I think he likes it. Looks like he's enjoying himself, and I hope you are too. I know that stuff can be a little bit weird. We'll talk about it in class. Pop back and take another look at it if you need to. Let's talk about alloys. So alloys are a blend of a metal with at least one other element, typically another metal, sometimes a non-metal. Really, almost all the metals that you come in contact with and use are alloys or blends. Like, for example, I have my ring here. You actually would not want a ring that was made of 100% gold unless you were just going to like melt it down and sell it. But if you actually wanted to wear it, gold is way too soft. So your ring would be misshapen after a day or two and you couldn't even wear it anymore. So other things are added to the gold to strengthen it. Steel, another example of an alloy. Steel always has iron and carbon in it, and then different elements depending on exactly what kind of steel. There's a ton of different kinds of steel, stainless steel and other kinds of steel. But steel is both lighter and stronger than iron. So like these huge buildings that we see, like skyscrapers and whatnot, you could not build those out of wood or iron. An iron building would collapse under its own weight if you tried to build a 100-story building out of iron. So we need steel to fuel a lot of these modern things that we have. Brass, which is like that shiny stuff like doorknobs, kind of decorative these days, or like a trumpet or something is often made of brass. Bronze was used a lot historically, if you think about the Bronze Age. Now, probably statues and things like that. You'll see some bronze things here and there, but statues are often made of bronze. pewter. This is a little pewter mug, I believe, here, which is tin, antimony, and copper. So a lot of different alloys, and we tweak the different metals involved depending on exactly what we want. Alloys are typically stronger than their component elements. So it actually decreases the malleability. The presence of foreign atoms in the lattice kind of disrupts. We were talking earlier about how these atoms can slide past each other. If there's foreign atoms in there, it actually disrupts that a little bit, which actually tends to make it a little bit stronger and more desirable often. Hey, and that's it. I hope you've enjoyed yourselves here. Thanks for talking with me and listening. I guess you're not really talking to me, but thanks for listening, and we'll see you next time.